Greetings, everyone. Time to talk about a few applications that go along with talking about the T and B frame, the tangent and the normal and the binormal vectors. Mostly the unit tangent and the unit normal vectors are the ones that we hit a lot here. But here's some applications that go along with that. Let's start with something familiar, right? The length of a curve. You've been doing that since Calculus 1. It's just the integral of the square root of the squares of the infinitesimal pieces at every given point, and you sum them all up by integrating, right? So if you convert that into vector notation, right, the vector functions have an x component and a y component, each of which would have their own derivative with respect to the variable argument, in this case t, with respect to t, right? So if I were to replace that, right, I'd have x prime and y prime each squared and added together, square rooted, right? Okay, and I'm using a sort of just a counter variable, dummy variable there. Notice the 0 to t, t being the point to which you're at on a curve, right? So t is just some point on the curve that you pick. It would be 0 up to that t. And basically what this does is it generalizes the length of a curve just a little bit more to it now being a function of t as well as the pieces of the vector function, right? So I have s of t is equal to this. But real quick, if you notice, the derivative of the x component and the y component, of course, this is in 2 dimensions. You can upgrade the same thing to 3D. It's the same idea. You would just have plus z prime of a squared also here. No difference in the terminology there. Okay, notice that what that really is just the integral of the length of the derivative vector function, right? Okay, so the length at any point t can be a function of t, right? From 0 up to t here, just be adding up all of the little bitty lengths of all the tangent vectors all the way along the curve. That's really all that is, okay? Little side note for later, don't forget that what this is implying is that s has a functional relationship to t. So I can actually take a derivative of s with respect to t also. And when I do, what I should get back is the length function, the magnitude function of the velocity vector, the tangent vector r prime, right? Should be the magnitude function of that one. Okay, so the length is something that we just find on things all the time, right? If I want to actually calculate one of these, which that would be handy, let's go ahead and calculate a length right here on this example, okay? So I'm going to start by finding the derivative with respect to t. So that would be negative sine t, cosine t, 1. Okay, so then from there, what I would want to do is find the length of that vector with respect to t, right? So it's just square root. I've got sine squared, right, because negative squared is positive, plus cosine squared of t, and plus 1 squared. But cosine squared plus sine squared is 1, right? 1 plus 1. What I'm ending up with here is square root of 2. Therefore, s of t is just going to be equal to the integral from 0 to t of the square root of 2, right? No actual variable there. dA, dy, dx, dt, just not dt, right? Because I'm already using t here. Okay. And that's just going to be equal to the square root of 2 times t. And this is what we're getting at. I can actually write s, the arc length, as a function of t, right? In this case, square root of 2 times t for this particular vector function, okay? And it should make sense to you why this is, because this actual vector function here is just the helix that coils around a unit circle while it climbs up the z-axis. So for example, what I mean is, if I've got this here as my x, y, and z axis, then this is just the helix that starts here on the x-axis and just coils around the z-axis like that. And the radius at any point, if you pick any point, like the distance from the z-axis is going to be 1. Okay? So I'm just constantly adding the same amount of arc length at any given point because it's literally wrapping around a circle there. Right? So I've got my velocity vector here, right? Got my normal vector pointing inward there. And it's just wrapping around and around like that. Okay. So next, the one of the things that we do with the arc length function, okay? Since it is a relationship between s and t, I can actually reverse it around and use that to replace t in my original function. Okay, so it's called reparameterizing a vector function, or actually any function, but in this case we're using vector functions. Okay, to reparameterize your original function by making and using that connection between t and s. And I will say, as a little side note here, this is easy in some functions and very, very difficult in other functions. And you'll see in a little bit, I'll show you a couple where it's really difficult to do this. Okay, but for this example right here, let's carry along, right? We have the relationship where s is equal to square root of 2 times t, right? S is equal to square root of 2 times t. That means that t would be equal to s divided by square root of 2, right? Okay, so use this fact to plug that back in to the original r vector function, right? Now technically right now, remember this one is r of t, right? And this is r prime of t, so on and so on. What I'm about to do is reparameterize r so that it is now a function of s, okay? R prime, not r prime, just r of s would then be the vector function cosine of something equal to t. So that would be s over square root of 2. Next, sine of s over square root of 2. And then just s over square root of 2 would be my reparameterized vector function. Okay, so Mr. Simon, why would we even care about doing that? We're leading up to something, watch. So now take your tangent vector, right? The tangent vector r prime. Now remember, this is not the same r prime as up here because this is technically dr dt, whereas this is going to be dr ds, right? So it's a different derivative, although it will be, related. Right here, when I take my derivative of each piece, notice what happens is I get a 1 over square root of 2 multiplied because of the chain rule there. Derivative of cosine is negative sine, and I still have s over square root of 2. So 1 over square root of 2 cosine s over square root of 2, and just 1 over square root of 2. All right. So right here, one of the things I'm going to show you that I want you to notice is that reparameterizing the original vector function and then finding that vector function's velocity vector, its derivative vector, its tangent vector here, will automatically give us a unit tangent vector without having to go through the process that we did last time of finding the derivative and dividing by its length. Here it's reparameterized with length, and therefore when you take that derivative you actually get a unit tangent vector. Okay, that's due to the way the arc length is changing with the function, right? So right here, that's what I want you to notice right here. Normally the derivative of r with respect to t is just a tangent vector, right? However, what we've just done, the derivative of r with respect to s, gives us a unit tangent vector. The length of this derivative function here, the magnitude, right, should be 1 no matter what, because of the way it's been reparameterized with the arc length. Okay, test that out. Look at it. The length of the r prime of s here. Okay, I can factor out a 1 over square root of 2. So I'll do that first. If I factor out a 1 over square root of 2, I pull that out. Then all I have to do is the length of the rest of the function pieces, which is going to be the sine, the cosine, and technically 1, right? Because I factored that piece out. So that would be the square root of the sine squared and the cosine squared. You should see where this is going, right? I'm going to get 1 plus 1 again, square root of 2 times 1 over square root of 2. I'm getting a length of 1. Okay? Well, this is good for us. This is a way that we can talk about a tangent vector being directly the derivative of some vector function, right? My vector function, parameterized with arc length instead of just some arbitrary t, gives us a unit tangent vector at every point as its own personal tangent vector. Okay, so that's sort of helpful, right? Sort of cool. Let's take it to that final step, the application that we're really interested in this section. Okay, something that probably has been hit around for a while, ever since Calc 1, and you've talked about second derivatives and concavity and things like that. One of the topics that we really need for later measurements of curves and eventually space, if you study differential geometry, is how is curves and how are curves and how is space bent, and how can I measure that and how can I quantify that? And that's where this comes in. That's where curvature comes in. Curvature being the actual calculation of how much something is not a line, right? That's basically what we're talking about here, right? A line would have 0 curvature, okay? So therefore, something that is not a line, things that are non-linear, anything other than a line, would have some sort of number for curvature. And it's going to be a positive number, okay? It's some sort of measurement of how non-linear it actually is. So here's the definition of it. Since the tangent vector with respect to s, right, is guaranteed as a unit tangent vector, okay, then the curvature is defined as the derivative of that tangent vector. Now let's think about that for a second. If tangent vector is always the same length, it's always a unit vector, right, then the derivative measures change. Well, it can't be that the vector's changing length, right? It's a unit vector. It's always length 1. Well, that's a very good way to measure the change in direction of something, right? So look over here on this curve. If you pick a point somewhere on here, okay, and it's been parameterized with s, then I get my unit tangent vector pointing along the curve, right? Right, we'll say that's t. Fine. As the point goes around, that tangent vector is going to turn, but the length stays the same. So the only thing that this derivative can be measuring is a change in the direction, or in other words, curvature, right? How is this thing changing the direction of the path? Okay? So the derivative of that unit tangent vector with respect to s because S is the piece that's guaranteeing that it's going to be a unit vector everywhere by itself. Okay? Or in other words, if I take the derivative of that tangent vector with respect to S directly, and then take the length of that, right? The magnitude of this vector quantity is going to measure and quantify curvature force. And that's what we're building up to here. So here we go. I've actually got my unit tangent vector here, right? That's this one, my R prime of S. So if you will, I can actually equate that with this T of S. This is my tangent vector of S. Okay, let's get this piece out of the way. We already know it's a unit vector. Okay, so what I really need to do then is take the derivative of that if I wish to find the curvature at some given point on my curve there. All right. So then T prime with respect to S is just going to be the derivatives of these again, right? I'll factor out, oh no, you know what? I'm not even going to factor out. Let's leave it like it is. I've got the 1 over square root of 2 that was already there, and it's going to bump out another one from another chain rule. So I'm going to have 1 over square root of 2 times 1 over square root of 2 times cosine S over square root of 2. Right? Well, that's just going to be 1/2. And the same thing's going to happen here, right? So I'll just write the 1/2 this time. Negative sign, though. And then derivative of a number, right, is 0. Okay, so my curvature is going to be equal to the length, the magnitude of this derivative that we just found, right? The length of this thing. Well, got a 0 squared, right? That's nice. And then I've got a 1/2 here and a 1/2 here. I mean, I could make it easy on ourselves and just factor that out at the beginning, right? Factor out the 1/2 at the beginning. Let's do that. Since they both have a 1/2 and a 1/2, I'm just going to factor that out, and since I'm doing a magnitude, it just gets the absolute value of that, right? The 1/2. And then I've got cosine squared plus sine squared. That seems to be the theme of this particular curve, doesn't it? And now you know why I picked it. Cosine squared plus sine squared, of course, is that 1 plus 0 is still 1. Square root of 1 is 1 times 1/2. So my curvature is 1/2. Now notice this was supposed to be of S, right? So K is being generic here, even though I found a numerical answer. All that's saying is every point on this particular curve has the same amount of curvature, okay? Well, of course, again, that makes sense. It's wrapping in a circular pattern, right? And it's increasing with the same length that it is using to wrap, right? So the curvature never changes. It wraps around basically a cylinder, right? You can take a piece of wire and wrap it around a cylinder. That's basically what you're going to get here, okay? So the curvature at any point for this one is just going to be 1/2. Go take a better look at this in GeoGebra real quick. Here's what that shape really looks like, much better than I can draw it. You can see it's the helix that's wrapping around the z-axis there. And I'm going to leave it like it is right now, 1:1, but in a minute I may squish it up so that you can see more of the helix. But I don't want to screw up the ratio of the axes here for right now. Let's take a look at the curvature. I have this thing calculating the curvature, and you can see it's 0.5. I have the initial point here starting when t is 0. Okay? And I'm going to hit play, and you're going to watch the thing travel up the spiral here. And then watch the curvature over here as it's happening. All right? Okay. See, the curvature is 0.5 and it's never changing. This curve has constant curvature at every point. But what is changing, you have to notice,
is the direction that the TNB frame is pointing, right? The TN plane is the interesting plane for us, and the B vector is just always pointing outward from the curve there. Notice the N vector is always pointing at that Z-axis from the curve, right? It's the center of rotation, and it's a circular rotation. You can see it slowly going around the circle when it's actually, climbing up the spiral there. Constant curvature.
Let's talk some more about curvature. We defined the curvature already to be the derivative of the tangent vector, the unit tangent vector, mind you, with respect to s, the arc length, right? So, as I was saying at the very beginning, I would have to reparameterize whatever function I'm using in order to build my way down to getting the tangent vector of s. Not many actually, there's lots of them out there where this is extremely difficult to do. So what we have are some alternate ways to calculate the curvature uh, using just your normal parameterization t, right? So the s was just a means to an ends here to make the connection in our minds why the curvature makes sense, but then most of the time we typically don't even use it because it's just much more difficult to do that reparameterization. Okay, so here's the original definition, right? dt ds, and the length of that, magnitude of that. Through a chain rule, you can actually say that that's the same thing as taking the derivative of the unit tangent vector with respect to t, the original parameter, divided by the derivative of the arc length with respect to t, which, if you think back to the very beginning, I told you on a side note real quick to remember the ds dt was equal to the length of the original tangent vector, right? So what I've got here is the length of the original unit tangent vector from last time that we talked about, that you just get through normal means, divided by the magnitude of your original tangent vector, right? So the length of the derivative of your unit tangent vector, that's where the change in direction is coming in. And then it just needs to be scaled by the arc length itself, right? That's the actual little piece of arc length. Okay, we can actually take it one step further than that, though. And this actually shouldn't come as much as a surprise because if you go back to last video on the TNB frames, I had that other way of calculating the normal vector in the unit normal vector, and it's very similar to this workaround here. I can actually take the length of the derivative of the unit tangent vector and show that it's the same as the cross product magnitude of the unit tangent vector and its derivative, right? And that's because the unit tangent vector is a unit vector, so it's length 1, and those two are guaranteed to be at 90 degrees to each other, so it's basically this length times that length times sine of 90, which is also 1, so it's the same thing as this, right? And then of course that length is still there, and not much of a stretch further from there, since the unit tangent vector comes from the derivative of the original vector function, and this derivative is somewhat related to the second derivative of that, right? So it's not much of a stretch. There's a little bit of a hand waving here because I'm saving some space, but you can see where it would make sense, right? And then it just needs to be scaled 3 times instead of once now. So I've got this formula is the one that we end up using a lot, because all it takes is a couple of derivatives of your original function, and then I just need the magnitude of that first derivative vector function, right? The length of the original tangent vector function cubed. Okay, so let's go over to our example that we just did a moment ago here, and let's use this formula now so that you can see it is going to be the same thing. So next I'll need r double prime, right? And I've got my derivative, negative cosine t, negative sine t, 0. And now I'm going to get the cross product of these two. So r prime cross r double prime. I've got my determinant, I, j, and k. Ooh. Okay. I've got negative sine t, cosine t, and 1. I've got negative cosine t, negative sine t, and 0. And now let's do our determinant here. For my I vector, I've got 0 plus sine. So sine. For the j, don't forget it's alternating, right? So this will be negative, but it's going to be 0 minus or negative cosine, right? So it would have been cosine, but it alternates back to negative. So negative cosine t. And then for the k, I've got sine squared minus negative cosine squared. So sine squared plus cosine squared is 1, right? And don't forget, this is a vector that should be perpendicular to both of those, right? You can go back and do the dot product and you'll definitely see that it is. It gives 0 through both of those dot products. Okay, and I just need a couple of lengths here now, right? We already did the length of this one earlier. Remember, we found the length of this one earlier to be square root of 2. 1 over it, right? No, it was square root of 2. Yeah. That's right. Because sine squared plus cosine squared, right? 1 plus 1 is square root of 2. All right. So now let's do the length of this guy here. The length of derivative of r crossed with second derivative of r is going to be square root of, we have sine squared, and I've got cosine squared, right? Sine squared plus cosine squared plus 1 squared is 1. Got 1 plus 1, I've got square root of 2, right? For that one. Okay, so now let's do the curvature calculation here. My curvature, k, is going to be this length, square root of 2, over that length, square root of 2 cubed, which, as you can see, still gives me the constant curvature of 1/2, right, as we calculated before. Okay, so while we're sitting here talking about this, one other thing that I just want to add in to this whole discussion of curvature is another connection to some of the geometry that goes in with it, okay? And that's called an osculating circle, right? Osculating. It's Latin for kissing, basically, right? So if there was such a thing as a tangent circle, if you will, hand waving there, this would be it, okay? The osculating circle is the circle that perfectly fits where the tangent vector of the curve is the same for that one point on itself and the circle, right? So the circle, the radius of the circle would have to be at a right angle, which, don't forget what that means. It means that the radius of the osculating circle then points in the direction of capital N, the unit normal vector, right? That helps if you're ever having to find it. Okay, and then the radius of the osculating circle is 1 over, it's the reciprocal of the curvature, okay? The circle itself perfectly fits into this small section of the curve, so that the curvature of the circle and the curvature of the curve itself are identical, okay? And so real quick, the curvature of just a circle you can get from an arc length formula easily. Circles have perfect curvature, okay? If I divide r to this side, and then I treat theta like a function of s, the arc length. Remember, we were doing functions of s to find curvature, right? So theta as a function of s, if I do d theta ds here, notice I get 1 over r. And it makes sense because theta can only do one thing, and that is change direction. So d theta ds represents how your tangent vector is turning on a circle, right? And it's perfect. It's the curvature of a circle is 1 over the radius of the circle. So therefore, anytime you know the curvature of something, that's also the 1 over the radius of the oscillating circle that fits snugly into that curve. Okay? So what does that mean over here, you think? The 1 over 2 is a constant curvature. That means you take a circle with radius 2, right? Radius, the reciprocal of this, and it should fit perfectly into the curve, into the niche right here. Let's say it's at this point. It would be a circle that would fit right perfectly into here, like this. And then the radius would be 2, okay? Well, think about it. The distance from here to here is 1 directly. So having a radius of 2 means that this circle, it would have to be way out here, right? It would have to be bigger than I have room for to draw here. And it would be at an angle. How do I know how the oscillating circle fits in there? Well, think about this for a second. The oscillating circle has to be at a right angle, and it has to have the same tangent, which means the circle itself would have to be with the tangent and the normal vector. So the TN plane, the unit tangent, the unit normal, the plane that those two make is always the plane that the oscillating circle resides in, which means the B vector is always going to be perpendicular to the oscillating circle, right? And it's going to fit into the nook of the curve there, okay? So before the next example, go take another quick look at the GeoGebra thing you can take and see what the oscillating circle looks like.
Same function. I'm starting it back at 0 again. But this time, instead of just looking at the curvature, right, which we have here, I also want you to take a notice of the oscillating circle, which is going to be the circle that fits into the curve as we discussed, right? It's going to be completely kissing and tangent to the curve there. So I'll turn on the center point for it, and I'll turn on the actual circle itself. Okay, so let me turn off the plane, and I'm also going to turn off the axes so we can focus on just the spiral. There's the oscillating circle for when t equals 0. Okay, if I turn this just right, you can see. You can't even distinguish the circle from the curve itself at this point right here. When it gets really close in, they're basically the same shape, which is why that circle and the curve are said to have the same curvature. And of course the radius is 1 over, so the radius is going to be 2. And don't forget, this curve has constant curvature. This curvature never changes, so the circle is actually never going to change size. Let's hit play and see what happens. The point's moving up the helix there, and then look, the circle is basically just following it, never changing size. It's almost rolling around the curve, if you will, but it's constantly fitting into the curve there. Another thing to notice, the circle's always in the TN plane, right? It's always perpendicular to that B vector, the binormal vector there. But it's a constant size. It's constantly radius of 2.
One more example of calculating some curvature here, okay? We have our vector function, and I want to talk about finding curvature at specific points now, when t equals 0 and 1, let's say. So 2 different points, let's find the curvature. And incidentally, that also means that we'll be talking about a certain size oscillating circle, right? And then I'll let you go take a look at that. So let's find the curvature function, and then we'll plug in some values of t. Okay, I'm going to use the second alternate version here, that is going to be the quickest route most of the time, right? You'll remember I used that other alternate to find n a lot. It's the easiest one for most of the vector functions we run into. So here we go. I'm going to do r prime 2t 2t squared 1 and r double prime. Yeah, we got 2, 4t, and 0, right? Okay. So now I want to find the cross product of these. So r of t crossed with r double prime of t. We have I, j, k, 2t, 2t squared, 1. Incidentally, if you watched my last video, you see that this is a function that we've already done this on. So this should look very familiar to you if you have. 0. Okay, so for my I right here, I've got 0 minus 4t. And then for j, I've got 0 minus 2, but alternate, so plus 2. And then for k, I've got 8t squared minus 4t squared. So 4t squared, like so. Okay? So I've got my cross product vector there. And I just need to find his length and the original tangent vector length right there. And we can calculate the curvature. All right. So the length of this guy is going to equal, well, let's make it easier on ourselves like we always do, right? I can factor a 2 out. Like that, which means I can just bring the 2 in front of my magnitude calculation. So then square root of, I have 4t squared, I've got 1, and I've got 4t to the 4th. Okay? You should recognize that if I rearrange the terms as something that I can factor into a perfect square, which we like to see, right? I'll have square root of 2t squared plus 1 squared, right? Okay? Which should then give me this as the magnitude of that cross product vector. All right. Real quick, look at the vector here. Negative 2t, 1, and 2t squared. Even though they're in different placements, right? You got 2t, you got 2t squared, and you got 1 with this vector, right? Well, what that means is, even though they're in different placements, of course they're going to be at a right angle to each other because they're crossed, but they're the same components. So when I do the magnitude of this guy right here, it's going to end up being the same thing because it's all the same pieces, just in a different order. But the magnitude calculation doesn't care about that. When I do this magnitude, I'm going to end up with this same setup, just, not with the 2. I'll just end up with this square root again, which is just going to give me the 2t squared plus 1, right? Okay. So my curvature is going to be this magnitude over this one cubed, which becomes 2 over 2t squared plus 1 squared for my curvature, right? Okay, so then when t is 0, my curvature is 2 over 1, 2. And when t equals 1, right, that was the other one we wanted to talk about, my curvature is going to be 2 over 2 plus 1 squared, 3 squared. So I get my curvature is 2/9. Okay? Now remember what that means. If I actually have this curve drawn out, right, then you should be thinking of, at that point, if I fit a circle into that curve, right? Our curve was something like that. It curved around and did something kooky in the middle there. It's hard to do like that. It did something like that, right? So at 0 it was here. I should be able to fit a circle in there, right? Such that the radius of that circle is 1 over this. Okay? One thing you need to notice is that as curvature increases, the radius of the circle decreases, right? And vice versa. If the curvature gets smaller, the radius of the circle gets larger. So notice at 0, I have a large curvature of 2, right? So I'll have a small circle of 1/2 radius squeezing into that piece of the curve, okay? But when the curvature decreases 2/9, and you do the reciprocal of that, right? Well, my circle is going to get bigger. It's going to have a bigger radius, right? 4.5 is the radius on that one. Let's go one step further. What happens to the curvature here as t goes to infinity? Take a limit of this as t goes to infinity. You'll notice the limit as t goes to infinity of 2 over 2t squared plus 1 all squared equals 0, right? Well, what does that mean? It means if you could go all the way out to infinity, right? If you could, we can't really do that, but as you go out, the curvature approaches 0. So this curve, as it goes further out, as t counts it out into infinity, it begins to just straighten out, right? So I have 0 curvature at infinity if I could get there, right? And think about what that means. 0 curvature would mean a straight line. What kind of oscillating circle would fit a straight line, do you think? Right? If I had a line, 0 curvature, what kind of circle would I need to fit that? Well, 1 over 0, right? If you take that limit, the radius is infinite, right? To fit an oscillating circle on something like that. So for this particular function, as t increases without bound, the curvature keeps getting smaller. For this curve, the circle is just going to keep getting larger as it goes out, right? The oscillating circle. The curvature goes to 0. Take a look at what this really looks like in GeoGebra. I hope this helps you understand curvature better.
Here's a much better version of that curve than the one I had drawn on there. The similar curve even to it's actually the same curve as the last video. As you can see, it spirals just slightly here up to the origin, and then it continues to spiral out this way again after it hits that origin point. It comes up, spirals, and then flakes out that way. Okay, and you can watch the vectors rotate here. See, B right now is pointing, the green vector B is pointing perpendicular to the Tn. And don't forget the normal vector has to point towards the bend there, right? So here we go, we're going to play it. See? Now watch the rotation, right? It's rotating, it's curving, and you have your curvature happening there, the major part of the curvature. Okay? I'm going to rewind it again, and I want you to take a look at this K value over here this time. That's the actual calculation of the curvature. Notice way over here, right, it's 0.07, a very small amount of curvature. And as I play it, you'll watch this curvature slowly get bigger and bigger. And as it gets really close to that middle, it starts to really get big fast. Right? Get up to that center point, and it peaks out at 2. Then it starts going back down again. Right? The curvature's lessening again as this curve starts to straighten out through the top portion of the path there. Most of the rotation has stopped as well. Okay, so again, the 2 points that we were interested in, let's take a look at those. That was when t was 0, right? That's this point right here. Notice the curvature is 2, as we calculated. And that means that the oscillating circle should be the circle that fits into this niche here and has a radius of 1/2. So let's see that one. Here's the oscillating circle center. There's that center point right there. And then here's the actual oscillating circle. There it is. Right there. Let's turn the plane off and see if we can see that better. All right. Let's turn the axes off too. There's the oscillating circle right there. See how it's basically kissing the curve. It's basically tangent itself in a way, right? Let's watch the oscillating circle change now as we, well, actually first, let's take a look at the other special point. We were looking at t equals 1, and that's this point on the curve right here. Notice the plane has rotated a bit. The oscillating circle should still be in the Tn plane, which is going to be here. Notice the center is way out here though, because my radius of that circle is much bigger. Here's that oscillating circle, and again, look, it shares this portion of the curve. It has the same curvature at this actual point. And it's a much bigger circle because it's a much smaller amount of curvature. Okay? So like I was saying, let's take a look at how the oscillating circle changes. I'm starting really far out on the negative end of t there. Look at how large that circle is. Such a small amount of curvature. The oscillating circle is huge in order to mimic that curvature. So I'm going to hit play here. I'm just going to let it go and then watch. As the curvature gets larger, you'll notice the circle is getting smaller. Here comes the center. It's centering in. And the circle itself is rotating the plane. Notice the circle is rotating in with the curve, hugging the curve the whole time. And there it goes. The curve is flattening out, so the curvature is decreasing and the oscillating circle radius is increasing to something really huge there. And of course, as this goes to infinity, as we saw, of course, the curvature does go to 0. So this circle just keeps getting bigger and bigger. Okay?